Welcome back to the Deep Dive, where we take complex engineering blueprints, tear them down to their strategic core, and really extract the most critical knowledge, saving you months of reading and development time.
And today we are in what is, it's probably the fastest moving sector of electric mobility, Formula Student Electric. The pace here isn't just fast, it's exponential.
Absolutely.
We're watching the competitive edge shift, away from brute mechanical strength and into pure electrical and algorithmic speed.
It's so true. If you look at the giants in this space, I'm talking about the global Tier 1 teams like AMZ Racing from ETH Zurich or, say, TU Delft, they've reached a point where the only thing left limiting their lap times is fundamental physics.
The tires, the track grip, that's the wall.
Exactly. So the battleground, it's not horsepower anymore, it's microseconds. It's control latency and perfect synchronization.
And that's the new reality. Our whole analysis today focuses on that.
Mm-hmm.
How does a new organization, one without years of legacy development, jump directly into that elite competitive space?
And that is our mission. We are diving into a really detailed motor control unit, or MCU, engineering requirements specification. This isn't just a standard parts list. This document was put together by a senior powertrain architect.
A strategic consultant, right. Over 25 years of experience in this specific field.
And it's meant to be a strategic blueprint. The goal is simple. For a new university team, how do you skip all the painful intermediate steps and immediately adopt that Tier 1 world-class standard?
To do that, we have to be really structured. We've used the McKinsey MECE framework, mutually exclusive, collectively exhaustive.
So breaking it down into clean, non-overlapping parts.
Exactly. We have to define 3 distinct, comprehensive areas that together make up the whole system.
Which are?
Okay, first, subsystem 5.1, the compute core. This is the brain. It has to be a heterogeneous architecture.
Okay.
Second, subsystem 5.2, the power stage. That's the muscle. And that means wide bandgap power electronics are non-negotiable.
And the third?
Subsystem 5.3, the communication network. Think of it as the nervous system, and it absolutely requires deterministic synchronization.
Okay, let's unpack all of this. But before we get into the nuts and bolts, we have to start with the big strategic question. This blueprint, it's incredibly aggressive. Why is adopting this high-end Tier 1 technology mandatory right from the start? Why shouldn't a new team just start simpler, learn the ropes, and then upgrade later?
That is the essential first challenge, and it's a good one. The impulse is always to start simple, but in FSE, simplicity, it just equals obsolescence.
So you're saying it's a trap?
It's a trap. To justify this aggressive blueprint, you first have to understand the competitive landscape you're walking into. We could break the field down into 3 architectural tiers.
Let's do it. Let's start at the bottom, Tier 3, the entry point.
Tier 3 teams, and this is where most new organizations start. They use reliable but utterly inflexible, off-the-shelf industrial inverters.
Things like a Sevcon.
Exactly.
Yeah.
Sevcon, maybe some Bamacar models. They're black boxes. They work, they're reliable, but you get almost zero access to the core control algorithms. That kills any potential for sophisticated dynamic vehicle control.
And what's their main technical limitation? I'm guessing speed?
It's switching frequency. They're often limited to less than 10 kilohertz. Plus, they are bulky and heavy, which is just poison for a race car. A team using this architecture, they might finish the endurance event, sure, but they will never, ever compete on lap times.
So they learn how to pass inspection, but they don't learn how to compete. Okay, so then you move up to Tier 2.
Tier 2 is the advanced, but ultimately it's the bottleneck group. These teams figure out they need custom control, so they move to controllers based on standard high-performance MCUs.
Like a TIC 2000 or a high-end STM32.
Yep, those are the usual suspects. They successfully implement field-oriented control, or FOC, which is a huge and necessary step, but they immediately hit a structural ceiling.
And that ceiling is the sequential processing bottleneck of that standard MCU architecture. Can you break down what that actually means for performance on the track?
It's just fundamental computer science applied to motor control. A standard MCU, even a really fast one, it executes instructions sequentially, one after the other. It has to process the current feedback, then run the coordinate transforms, then execute the PI controllers, then generate the space vector modulation, and then finally update the PWM registers.
All in a line?
All in a line. And that sequential nature inherently limits their current loop update frequency. You're looking at a hard ceiling in the 20 to 30 kilohertz range.
Okay, so what are the real-world consequences of being stuck at 30 kilohertz? Why can't you win a race with that?
The problem is twofold, and it links directly to the kinds of motors you see in modern FSE cars. These motors are designed for insane power density, which usually means they have very low inductance.
And low-inductance motors need faster switching.
Much faster. At 30 kilohertz, you get significant current ripple. And that ripple, it's not just an electrical artifact. It translates directly into things you can feel and measure. Motor vibration, an audible whine, and critically huge power losses. Just heat.
So you're just burning energy to make noise and heat, and you need a bigger cooling system to deal with it?
Exactly. You end up in this vicious cycle, trading efficiency for speed, and your control just feels sluggish. It's not responsive enough.
So Tier 2 is basically a performance dead end. It takes a team maybe 2 years to develop, only to realize their car can't handle the dynamic demands of a world-class lap time.
Precisely. And then try to synchronize 4 of those 30 kilohertz controllers for precise torque vectoring. It's almost impossible because of all the communication jitter and those sequential delays. That's the 30 kilohertz ceiling. It's an architectural limit, not a software bug you can fix.
Which brings us to Tier 1, the elite standard. This is the blueprint we're actually defining today.
Tier 1 teams, they abandoned that standard MCU bottleneck years ago. Their whole strategy is about breakthroughs in materials, science, and parallel computing. They use a heterogeneous system on chip, or SoC architecture.
An FPGA.
Specifically, and SoC and FPGA, combined with Silicon Carbide or SoC power elements. And that combination is what lets them push the current loop bandwidth way past 100 kilohertz.
Okay, I have to challenge you on this, though. Speaking for a new team, they're facing this massive complexity curve. And you're telling them to directly adopt the Tier 1 path. That requires advanced skills in FPGA development and high-frequency power electronics. You're telling them to skip the learning phase entirely. Isn't that a recipe for immediate catastrophic failure?
It's the only strategy that guarantees long-term success. A new team aiming for the podium, he simply cannot afford the 4 years it would take to design a Tier 2 system, race it, realize it's a dead end, abandon it, and then start over.
So this blueprint, the Powertrain 5.0 architecture, it's about leapfrogging that wasted time.
Exactly. It's an investment in future competitive relevance from day one.
That makes the distinction essential. So let's define this 5.0 architecture using its core philosophy, which is this software-defined powertrain built on this idea of fast loop, slow loop separation.
This separation is absolutely foundational. The fast loop handles all the hard, deterministic, high-speed control tasks. We're talking timescales of less than 10 microseconds.
So what's in that loop?
The ADC sampling, the core FOC Matthew or Clark and Park, transforms, the PI current control, and the space vector modulation generation. And crucially, all the hardware-level protection mechanisms also have to live here.
And because of that sub-10 microsecond requirement, this loop has to live where, specifically?
Entirely within the dedicated parallel execution architecture of the FPGA, what we call the programmable logic, or PL, side of our SODI. It has to execute instantly and with zero jitter.
And then the slow loop takes all the other computational load off that critical path.
Precisely. The slow loop operates on a much more relaxed timescale. Think 100 microseconds up to a millisecond. These are tasks that need more computational flexibility but are less sensitive to microsecond timing.
Like the outer speed control loop.
Right. The speed loop, complex algorithms for flux observation, thermal management strategies like, dynamically derating power based on motor temperature, and managing the high-level communication stacks like EtherCAT and CAN.
And these tasks are given to the more flexible general-purpose processor, the ARM side, or the processing system. So if we connect this to the big picture, why is this segregation so revolutionary compared to just using a single, really fast DSP to do everything?
Because it guarantees hard real-time performance. When you move those fast deterministic tasks into the hardware, into the PL, you eliminate the single biggest failure point of traditional systems. The communication bottleneck and the non-deterministic nature of software interrupts.
So for something like torque vectoring,
for sophisticated vehicle dynamics, especially four-wheel torque vectoring, where you are balancing the car on the absolute knife edge of tire adhesion, that hard real-time guarantee in the microsecond range is the difference between generating a precise yaw moment and just spinning out of control.
Okay, so let's talk about the brain that enables this split. Subsystem 5.1, the heterogeneous compute core. The blueprint mandates the AMD Zynq-7000 SoC. Why this specific chip? Why is it so essential for Tier 1?
The Zynq is the mandatory choice because, frankly, it's the most mature and capable platform for achieving this PL-PS separation in a single device. It combines a dual-core ARM Cortex-A9 processor, that's the PS, with the high-speed Arctic 7 FPGA fabric, the PL. And this isn't just two chips glued together, it's a deeply integrated system.
And this specific model recommendation, the XE7 Z20 or the 015, Why should a team invest in the larger chip right now? It's more expensive.
Yeah, but the resource justification is crucial for the long term. The XE7 Z020 offers you about 85,000 FPGA logic cells and 220 dedicated DSP slices. You need that margin. The FOC is just the beginning.
Right.
You also have to implement complex observer models, high-gain observers, maybe even calling in filters for accurate flux estimation, and you absolutely have to leave significant margin for future development.
So we're planning for a future where the controller might integrate, say, predictive maintenance or advanced sensor fusion algorithms.
Precisely. You could go with the smaller Z7010, save a little money up front, but you'd be hamstringing your future. You'd be forcing a painful, multi-year architectural migration when you inevitably realize you need those extra logic cells for that next level feature.
What's a good utilization target then?
We estimate that even with the FOC core, the observers, and the safety logic all implemented, you should only be targeting maybe 40–50% utilization of the Zynq-7020's resources. That ensures your long-term viability.
The core advantage is clearly partitioning tasks for hard versus soft real-time. Let's dive deeper into the PL side, the Arctic 7 FPGA, the true hard real-time engine.
The PL is where you win or lose the competition, because the FOC is the heart of motor control, the entire mathematical core, your Clark, Park, and inverse Park transforms, and the critical PI current controllers must be hard-coded into the FPGA fabric.
Using a hardware description language.
Right. And that allows for parallel execution. All these math steps happen simultaneously, not one after the other.
And this leads us to what is probably the most aggressive performance KPI in the entire blueprint.
It is the total loop latency. That's the time from the ADC converting the raw current sample to the PWM duty cycle update actually hitting the gate driver. That entire chain must be less than 10 microseconds.
And that number isn't arbitrary.
Not at all. That aggressive target is what supports the necessary 100 kilohertz current control frequency.
Why does hitting 100 kilohertz matter so much for the actual control quality? What does the driver feel?
Remember that current ripple we talked about with the Tier 2 systems? By operating at 100 kilohertz, we're switching 10 times faster. This allows the controller to react 10 times faster to any disturbance. More importantly, it keeps the current incredibly smooth.
And smoother current means?
Less wasted energy is heat, higher efficiency, and a motor that runs cleaner and more predictably under high load. For the driver, it translates directly to better control authority. The car does exactly what they want, instantly.
How do you actually achieve that 10 microsecond latency target in the hardware? It sounds almost impossible.
It requires meticulous optimization of the FPGA's resources. You have to leverage the dedicated hardware blocks that AMD provides, specifically the DSP-48 slices. These are custom hardware blocks designed purely for multiply-accumulate operations.
The core of any PI controller math.
The absolute core. You use these for the highest speed signal processing.
And what about the trigonometry, the sines and cosines for the Park transforms?
You definitely don't use general logic gates for that. It's too slow. Engineers rely on either Cordic algorithms, which stands for Coordinate Rotation Digital Computer, highly efficient for this in hardware, or they use highly optimized lookup tables, LUTs. This parallel dedicated execution path is the only way you meet that 10 microsecond deadline.
And you mentioned leaving margin here too.
Always. We aim for very low utilization of the DSP slices, maybe 15–20%, again, to prioritize margin and leave room for future safety logic integration.
Okay, speaking of safety, let's turn to the most critical requirement for the PL hardware level safety. The blueprint mandates that overcurrent, overvoltage, and desaturation fault protection must reside entirely in the FPGA. Why the absolute necessity of putting safety logic in hardware?
Because of the physics of failure. These modern wide bandgap components, especially SiSi, have an almost instantaneous failure mode. When a catastrophic short circuit happens, we are talking about component destruction in 1 to 3 microseconds.
So if you relied on software, what happens in that time?
The software, running on the ARM processor, it relies on interrupts. The software has to stop what it's doing, save its state, load the interrupt service routine, execute the protection code, and then send a command to shut down the PWMs.
That sounds slow.
That entire chain involves overhead, latency, and, crucially, jitter. Even in a best-case scenario, you're looking at tens of microseconds, which is an eternity. The CNZAP module is destroyed before the software even finishes loading its protection routine.
So the mandate is clear.
The mandate is absolute. The FPGA must detect the fault using dedicated comparators and block the PWM output. A hard power cut in the 100 nanosecond range. It's a direct hardware response, completely bypassing the non-deterministic software layer. This is not optional. It is fundamental for component survival.
And for the FSC to work, we also need instantaneous, high-precision position data.
Yes, the rotor angle accuracy is foundational. The PL has to manage the real-time decoding of the motor's position sensor. Whether the team chooses a robust resolver or a high-resolution absolute encoder like an NDET or BS, the PL processes those signals immediately.
Any delay is catastrophic.
Any phase lag in calculating that rotor angle, theta, will instantly decouple the magnetic fields, destroying all the efficiency you gained from using FOC in the first place. The speed of the PL ensures you have instantaneous position information, always.
All right, let's move to the other half of the heterogeneous core, the ARM-based processing system, which handles the dynamic management and communication. What's the system's role here, and what about the choice of operating system?
The PS is the strategic commander. The OS choice really depends on the team's priority. We recommend FreeTOS if the team prioritizes absolute minimal context switching latency for their high-level loops.
So pure speed.
Pure speed. Alternatively, a real-time patched embedded Linux gives you a much more robust, feature-rich environment. And that's hugely beneficial if you need advanced network stack support, especially for acting as an EtherCAT master.
So what are the key strategic tasks that the ARM processor is handling?
The PS handles the outer loops and the overall strategy. Task 1 is the speed loop control. It takes the driver's throttle input, compares it to the motor speed, and calculates the required torque command. That becomes the coaxis current command, ICHE.
Okay.
Second, field weakening control. It calculates the required negative D-axis current command, IDAGA, which you need to extend the motor's operating speed beyond its nominal base speed. Absolutely crucial for long straights.
And thermal management.
Vital. The PS is constantly monitoring all the motor and inverter temperatures. It's executing the complex thermal derating strategies, and it's managing the big communication protocol stacks like EtherCAT and CAN. Essentially, the PS translates the driver's and the VCU's intent into commands and registers that the FPGA can then execute at maximum speed.
Now, this is where the integration gets tricky. You have two separate processing domains running at vastly different speeds, one in nanoseconds, one in milliseconds, and they have to constantly exchange data. How does the internal interconnect, the AXI bus, prevent a new bottleneck from forming right there?
The XI bus is the high-speed highway that links these two worlds. And it's not just one single interface. It's a whole family of interfaces tailored for different data types. We rely on 3 specific AXI types to optimize how data moves.
Can you give us an analogy to keep this clear? Let's compare the data movement to, say, human communication needs.
That's a great way to think about it. First, you have AXI light. Think of this like sending a short text message or adjusting a thermostat on the wall. It's used for low-speed configuration data.
Like FOC gains.
Exactly. The ARM processor reading a status register on the FPGA or updating the FOC gain coefficients. Low bandwidth, but immediate access.
Then you have the high-speed data streams, like raw sensor readings.
For that, you use AXI HP, the high-performance ports. This is like streaming a 4K video directly to a dedicated memory buffer. The PL streams massive volumes of high-speed data raw ADC samples, telemetry logs, observer states directly into the DDR memory without clogging up the CPU cores. That data is essential for post-run analysis and debugging.
And the third one, the AXI ACP, the accelerator coherency port.
This is the critical synchronized communication path. The ACP ensures cache coherency. Imagine the ARM processor calculates a new critical torque command. That command needs to be instantly visible and consistent in the FPGA's own cache. The ACP guarantees that data moving between the PL and PS is synchronized with the CPU's L2 cache, which eliminates the delay and the risk of the FPGA acting on stale data. It's the most critical link for closing the control loop safely.
Okay, we've established the complexity of the hardware is immense. You're integrating C code, maybe Linux, and FPGA firmware. For a new university team, the development workflow is just as critical as the hardware selection. The blueprint mandates model-based design, MBD.
MBD is the secret weapon for managing this complexity, especially with student turnover. Manually writing and debugging millions of lines of C code interacting with VHDL or Verilog logic, it's just untenable under the time pressure of an FSE season. So we mandate the adoption of the MathWorks Simulink toolchain.
What's the core advantage here, beyond just, better code generation?
It standardizes the design process and it enforces structure. The team models the entire control system's behavior, the FOC, the observers, the state machine, visually in Simulink. The code generation tools then take that validated behavioral model and automatically generate the highly optimized platform-specific code.
So HDL Coder generates the hardware logic for the FPGA.
Correct. HDL Coder spits out the necessary Verilog, or VHDL, for the parallel execution on the PL. And then embedded coder generates the optimized C, or C++ for the PS. This ensures consistency and correctness across both domains. It just drastically reduces manual coding errors and accelerates your iteration cycle. If you change control in the model, you push a button, and the code for both sides is updated.
This feeds directly into the requirement for maintaining a golden reference model. What exactly is this model, and why is it so vital?
The golden reference model is the entire control system simulated purely in software. It's the mathematical ideal. It serves as the unimpeachable ground truth. Before you deploy any generated hardware or software code onto the real Zynq chip, you have to run side-by-side verification tests. You compare the behavior of the generated code against the ideal behavior of that golden reference model.
It sounds like the ultimate quality check.
It is. If the generated code deviates from the model's behavior in simulation, you know you have an issue. A quantization error, a timing problem, a transformation mistake, before you ever commit to expensive and dangerous physical testing. This front-loading of verification can save you weeks of debugging time on the track, and frankly, it protects the hardware budget.
Okay, here's where it gets really interesting for me. We've talked about the cutting-edge brain, subsystem 5.1. Now let's talk about the muscle, subsystem 5.2, the power stage revolution, which mandates the shift to silicon carbide or SiC MOSFETs. This feels like a fundamental materials science requirement for Tier 1 performance.
It is. If you stick with traditional silicon IGBTs, you simply cannot hit the power density and efficiency targets that you need for a competitive FSE car. SIA is the material science breakthrough that enabled that 100 kHz control loop we defined earlier.
So what are the fundamental physical advantages that SiC provides that make it mandatory?
Zynq fundamentally alters three key properties compared to standard silicon. First, it has a 10 times higher breakdown field strength. That lets you use thinner layers for higher voltages. Second, about 3 times higher thermal conductivity, so heat moves away from the active switching area much faster.
And the third?
And third, and this is the most important part for our speed target, it has much lower switching losses, especially at high frequencies.
What does that actually translate to in terms of the race car's performance and packaging? How does it make the car faster?
It translates directly to the goal of high power density. Because CC can switch so fast and so efficiently, the team can dramatically shrink the physical passive components. I'm talking about the bulky DC link capacitors and the large heat sinks that typically dominate an inverter's volume.
A smaller, lighter inverter.
The goal is an inverter volume reduction of 30 to 77%. You're aiming for an aggressive power density target of 20 to 30 kilowatts per liter. This density is crucial for packaging the inverter inside the extremely constrained aerodynamic envelope of a Formula Student car, especially when you're using 4 individual wheel-end MCUs.
Okay, now we come to what seems like a counterintuitive selection. The blueprint requires 1200-volt rated SuperC components, even though the FSE bus voltages almost never exceed 600 volts.
Yeah.
This seems like massive overkill. What's the engineering rationale here?
It is a non-negotiable safety and performance margin that comes from fundamental physics. As we said, 6C switches ultra-fast. That means the rate of current change to Cs is huge.
Right.
Even the smallest amount of stray inductance, stray in the circuit, which is impossible to eliminate entirely, when you multiply that by a massive steep, you generate enormous transient voltage spikes.
So phi spike equals Zeiser's errors. The faster you switch, the bigger the spike.
Precisely. In a 600-volt system with aggressive switching, those transient spikes can easily exceed 800 volts. They can hit 900 volts. If the team selects cheaper 650-volt rated components, they immediately enter the danger zone.
And they'd be forced to slow down the switching.
They'd be forced to artificially limit the 6E's switching speed, slowing down the DT to manage that voltage spike, and in doing so, they sacrifice the core performance advantage they invested in the first place. By mandating 1200V components, from manufacturers like Wolfspeed, their C3M series is a good example, we ensure a robust safety margin. It allows the team to push for the most aggressive, highest efficiency switching strategies without fear of immediate component destruction.
The 6E module is the power element, but the gate driver is where the control intelligence meets that raw power. This design has to be incredibly rigorous. The first requirement is the mandatory use of a negative turn-off bias.
This requirement goes right back to the low threshold voltage of 6E. Most 6E MOSFETs have a threshold voltage, VGSA, of only 2 to 3 volt. It's very low.
So it's easy to accidentally turn on.
Exactly. When the high side switch in an inverter leg turns on, the voltage change across the lower switch is incredibly fast. That's the high BVTT dial. This rapid voltage change couples energy through the internal gate-to-drain capacitance of that lower switch. We call it the Miller effect.
And that can turn the bottom switch on when it's supposed to be off?
Correct. That energy coupling can induce a voltage spike on the gate high enough to momentarily cross that low 2-3-volt threshold. That causes a spurious, unintended turn-on, what we call shoot-through.
Which means the high side and low side are conducting at the same time, instantly shorting the DC link.
A catastrophic failure. The negative bias, typically Melico 4V to Menafors 5V, acts as a powerful low-impedance lock. It aggressively pulls the gate voltage below zero and prevents that Miller coupling from ever crossing the threshold. It is essential for reliable high-frequency operation.
Beyond the bias, the blueprint also recommends integrating an active Miller clamp.
The active Miller clamp is an extra safety measure. It provides an ultra-low impedance path to ground during that crucial turn-off transient. It just ensures that any disturbance induced by the Miller effect is suppressed immediately, maintaining complete control integrity.
Okay, let's circle back to safety speed. The blueprint mandates ultra-fast DESET protection. Why is the speed requirement here even stricter than with traditional components?
Because the physical short circuit withstand time of size is terrifyingly short. We're talking 2 to 3 microseconds, maximum. Unlike an old IGBT that might tolerate a short for 10 microseconds, a SiCGET component will fail, often violently, in that tiny 2-3 microsecond window.
So the desaturation detection circuit has to act even faster than the physical failure time.
It's a race against physics. The DESET circuit has to detect the high current condition, indicate the fault, and trigger the gate driver to cut the power within 1 to 2 microseconds max. If you miss that window, you've just converted a $2,000 power module into a pile of melted silicon and smoke.
A lesson every top team has learned the hard way.
Through very expensive failures, yes.
We discussed EMI earlier. The gate driver also has specific requirements to deal with the electrical noise generated by the SiCGET.
Yes. The extremely high DDDT, we are talking tens of thousands of volts per microsecond. It generates massive displacement currents. These require the isolation drivers to maintain absolute signal integrity. The isolation components have to meet a high common mode transient immunity, or CMTI, standard, greater than 100 kilovolts per microsecond.
And if the CMTI isn't high enough,
those displacement currents leak across the isolation barrier, they corrupt the sensitive low-voltage control signals, and they cause driver misfires or lockups. It's a critical spec.
Finally, the physical mechanical design has to support this level of performance. Talk about the low inductance bus bar requirement.
A physical layout is just as important as the silicon itself. To manage those massive voltage spikes from the high DDA, you have to minimize the stray inductance, low power loop between your DC link capacitors and the power module. The blueprint mandates laminated bus bars.
So sandwiching the positive and negative conductors close together.
Exactly. You connect these components with laminated bus bars, and you target a loop inductance of less than 10 nanohenries. This is a highly aggressive physical requirement. It demands custom manufacturing and very precise assembly.
And for thermal management, since SiC runs so much hotter and denser,
you need maximum heat removal. The recommendation is pin-fin liquid cooling base plates. Instead of simple flat channels, this structure uses arrays of vertical pins. It dramatically increases the effective surface area for heat exchange and promotes active fluid turbulence.
Which is key for pulling heat away from the small, sexy chip area.
Essential. We also recommend using Kelvin source packaging on the SiC module itself. It's a 4-pin package that creates separate physical connections for the high current power loop and the sensitive low current gate drive loop. This further optimizes switching and reduces noise coupling.
So we have the brain and the muscle built for microsecond speed. Now we need the nervous system, subsystem 5.3, the communication network. For a modern FSD card, this means coordinating four-wheel and motors absolutely perfectly.
That is the ultimate challenge, four-wheel torque vectoring. If you send a command for 50 Newton meters of torque, and the front left motor executes it 50 microseconds late compared to the front right motor, you've just generated an unwanted, unpredictable yaw moment.
And when the car is at the limit of handling, that jitter.
That jitter causes an immediate loss of control. The network has to be deterministic. That means no packet loss and, crucially, no variance in arrival time.
The blueprint mandates a dual-bus architecture with EtherCAT as the primary control link. Why is EtherCAT the critical foundational choice for elite performance, replacing protocols like CAN?
Because of one specific feature. The distributed clocks mechanism embedded in the EtherCAT protocol. Traditional systems, they rely on the master VCU to send a timestamp and just hope all the slaves receive and execute at the same time. This introduces huge jitter.
And EtherCAT works differently.
completely differently. In EtherCAT, all the network nodes share a synchronized global clock. This mechanism ensures the synchronization error between all nodes is extremely low, typically less than 1 microsecond. This microsecond precision is the absolute prerequisite for effective, predictable torque vectoring. It provides a precise time base for coordinating the PWM phases of all 4 inverters.
How is this demanding protocol implemented within our Zynq SoC architecture?
It has to be implemented in the fastest section. The team must integrate the EtherCAT slave controller, or ESC, IP core backoff, provides a good one, for example, directly into the Zynq's programmable logic, into the PL.
Why in the FPGA and not just in the ARM processor's software stack?
The secret of EtherCAT is its on-the-fly processing. The data frame is processed as it passes through the node. It's not consumed and retransmitted by the CPU. Integrating the ESC IP core into the PL allows the network processing to happen in hardware at near zero latency. That gives you true hard real-time performance that a software-based implementation simply cannot match.
So, if EtherCAT is handling the critical control, what role does the secondary link CNFD play?
CNFD is essential for robustness, compliance, and all the secondary data. It offers significantly higher bandwidth than classic CAN, up to 8 megabits per second, with 64-byte payloads. This bandwidth is crucial for transmitting large volumes of non-real-time diagnostic data.
Like temperature logs.
Extensive temperature logs, detailed error codes, battery management system status, motor observer diagnostics, all the heavy data that you need for analysis, but that isn't time critical.
And this fulfills a crucial regulatory role as well, right?
Yes. Competition rules, especially from Formula Student Germany, often mandate a CAN broadcast for external data loggers and supervisory systems. Using CAN-FD ensures you meet this compliance requirement easily. It also uses a much more robust error checking system, a CRC17 or CRC21 algorithm, which is vital for maintaining data safety in the high EMI environment we've created.
The communication system serves the algorithms that actually drive the car. The MCU has to be ready to handle 1,000 Hz torque allocation commands from the vehicle control unit. Describe the required torque vectoring strategy the MCU needs to execute.
The VCU calculates the required total torque based on driver input and high-level dynamics models. The TV strategy, which usually uses algorithms like PI-yaw rate tracking or more advanced LQR, then dynamically distributes that torque across the 4 wheels to generate a specific calculated yaw moment, a turning force.
And the MCU has to execute that every millisecond.
Every millisecond, without fail. It has to be fast enough to execute these subtle, continuous adjustments at 1,000 Hz.
And the regulatory constraints here are critical for the control logic.
Absolutely critical for safety and for passing tech inspection. The FSG rules, specifically T11.8.9, stipulate that the TV control algorithm is only legally allowed to subtract torque from the driver's total requested torque.
It can't add power.
It cannot actively add power or generate acceleration that wasn't requested by the accelerator pedal. This hard constraint has to be meticulously implemented in the high-level PS logic to prevent any unexpected vehicle behavior. That would lead to an immediate disqualification.
Finally, traction control. Maximizing acceleration requires an instantaneous TC reaction.
Traction control has to live in the hard real-time layer, just like our core safety logic. The slip rate estimation, the difference between motor speed and vehicle speed, has to use the FPGA hardware counters for maximum speed and precision.
And the response.
If excessive wheel slip is detected, the command to reduce current has to be implemented directly as a current limit adjustment in the FPGA layer, in the PL. This guarantees the fastest possible response, minimizing wheel spin and maximizing your limited track time for the acceleration event. If the PS were involved, even for a few milliseconds, you'd lose too much grip.
So we've created this incredibly fast, high-power system. We have 100 kilohertz switching, 1,200 V components, sensitive Zynq logic, all running side by side. You mentioned earlier that SiC creates an EMI nightmare. So how do we ensure signal integrity and electrical safety when we're dealing with so much interference?
The success of the entire system hinges on mastering electromagnetic interference, or EMI, suppression. The high-frequency switching generates intense radiated and conducted noise. If you fail here, your low-voltage sensors will fail, the Zynq will reset, and the car will just stop.
So how do you mitigate it?
To mitigate the conducted noise, the blueprint mandates the design of LCL, or CLC, that's a pi-type hybrid EMI, filters right at the high-voltage DC input. These filters work aggressively to filter out both differential mode and common mode noise generated by the inverter.
And common mode noise is the specific difficulty posed by SiC's rapid switching.
It is the absolute pain point. 6 ultra-high DVDT day causes energy to couple through the parasitic capacitance that exists between the motor windings and the motor housing, which is often tied to the car chassis. This creates huge common mode leakage currents that flow through the vehicle structure.
How do you fight that?
You need high-quality common mode chokes and white capacitors, which connect the power stage to the chassis or protective earth.
And what happens if a team fails to suppress this common mode noise adequately?
The consequences are severe. First, the noise will couple into every piece of low-voltage wiring, corrupting CAN signals and confusing the zinc. Second, and crucially for compliance, that leakage current can easily trip the vehicle's mandatory insulation monitoring device, the IMD.
And if the IMD trips?
The car is immediately disqualified, either during technical inspection or worse, during the endurance event.
Beyond noise, we have to ensure absolute physical safety and compliance with the FSG rules.
Safety is paramount. The team has to adhere strictly to FSG rules, like EV 4.3, on the physical separation and isolation between high-voltage and low-voltage systems. The most critical dimension here is creepage distance.
Remind us what creepage is.
Creepage is the shortest path along the surface of an insulating material, like a PCB, between two conductive parts. For a 600-volt system, the PCB must maintain a minimum 4.0 millimeter creepage distance to prevent surface flashover, arcing, or tracking from contamination.
And how do you guarantee this, especially when you're building dense, compact boards?
The recommended strategy is proactive physical modification. PCB milling slots. The team should design and manufacture the board to include intentional small cuts or air gaps milling slots between the high-voltage traces. This dramatically increases the effective creepage distance, ensuring the board passes that stringent technical inspection process and maintains robust safety margins, even in humid track conditions.
And isolators.
All signals that cross the HVLV boundary PWM signals, voltage sampling feedback, all of it, must use high reliability, automotive-grade digital isolators rated for more than 3,000 VRMs, no exceptions.
Building a system of this complexity, it demands a validation strategy that matches the technical ambition. The blueprint requires adopting the V-model development process to ensure the extreme reliability you need for that 22-kilometer endurance event.
The V-model moving systematically from requirements down to component testing and then back up through integration testing to system validation is non-negotiable for system reliability. But within that model, Phase 2, hardware in the loop or HIL testing, is the single most important step for a student team.
Why is HIL testing mandatory before connecting the Zynq controller to the actual Syntel inverter? This is a massive investment in simulation technology.
Because the Synges modules are expensive, they're fragile, and they're incredibly easy to destroy. A new team cannot afford to learn through component failure. The HIL simulator, whether it's a custom solution or a platform like Typhoon HIL or SpeedGoat, it simulates the entire complex power stage.
The motor, the switching?
The motor model, the switching harmonics, even the noise on the sensor lines, all in a completely zero-risk virtual environment.
So it's a dry run for the most dangerous part of the system. What specific risks does HIL eliminate?
It eliminates the risk of frying your hardware because of a logic or timing error. You can test catastrophic faults that you could never safely test on the real car. You can simulate a short circuit, an encoder loss, a communication failure, extreme power surges, and e-stop trigger. HIL is statistically proven to detect up to 90% of all software logic and critical timing errors.
So the team is debugging the algorithm and the logic, not the physical hardware.
Exactly. HIL testing is the secret to the high completion rates of the top teams. If you burn out a Santa module during track debugging, you lose $2,000 and 2 weeks waiting for replacement parts. If you catch that same failure in HIL, you lose 30 minutes of simulation time. It saves budget, it maximizes your scarce track testing time, and it fosters that first-time right ethos.
And once HIL is complete and the logic is validated, we move to Phase 3, dyno calibration.
The dynamometer is the final physical validation step. You use it to precisely measure the motor's specific electrical parameters. The D-axis inductance, Larawal dollars, the Y-axis inductance, Larawal, and the flux linkage, lambda. Even motors of the same model can vary slightly.
And this data fine-tunes the controller.
This precise data is then used to fine-tune the core FOC-PI controller parameters and accurately calibrate the field weakening curves that you need for high-speed operation. You cannot achieve peak efficiency without this precise physical calibration.
This entire specification is a Tier 1 technical roadmap, but you've also applied the McKinsey 7S framework strategy, structure, systems, skills, staff, style, and shared values to this process. This suggests the technology is secondary to the organizational structure. Why is that alignment so critical?
Because an engineering team, especially a university team that faces rapid student turnover and fixed timelines, is a dynamic system. You can specify the Zynq, but if the team structure or the skills don't align with that choice, the project will fail. The 7S framework forces the team to align the soft S's, the people and the culture, with the hard S's, the technology and the systems.
Let's look at the core elements required to support this blueprint, starting with strategy.
The strategy has to be unambiguous. Focus on high power density and algorithmic leadership. This means every single development decision has to prioritize SiC efficiency and Zynq algorithmic optimization. If a simpler off-the-shelf component is proposed, it has to be rejected because it violates the long-term strategy. The team has to avoid distraction and commit fully.
What skills must this new team aggressively recruit for or train?
The skills have to be cross-disciplinary, reflecting the nature of this heterogeneous architecture. A team can no longer be segmented into just electrical and mechanical. They need deep expertise in FPGA development Verilog, or VHDL. They need specialized knowledge of high-frequency power electronics, understanding C-on-C physics, and gate driving. They can advance control theory to implement FOC, observers, and TV algorithms. And critically, they need proficiency in vehicle dynamic simulation to properly tune the torque vectoring logic. You need engineers who can speak across all those boundaries.
And the shared value, the organizational ethos that guides the work, you define it as first time right.
First time right is the antidote to the pressures of FSE racing. It means prioritizing verification and validation over the speed of implementation. This value is realized through mandatory front-loaded simulation MBD and agile testing. The shared understanding has to be that time spent in simulation and modeling is time saved in track debugging and component replacement. It is about intellectual rigor, which saves the team time, money, and maximizes the use of their scarcest resource, track access.
What's fascinating here is that the blueprint isn't just about winning races today, but about what the engineers learn for their careers.
Absolutely. We are essentially forcing the development of competencies that are foundational to the future of the global automotive industry. Heterogeneous computing, wide bandgap electronics, software-defined vehicle architectures, these are not niche anymore. They are the core competencies required for the next generation of production electric vehicles. By mastering this Tier 1 blueprint, the team is graduating engineers who are ready to lead the future of transport.
We have charted a path that skips the traditional learning curve and dives directly into the cutting edge of electric motorsport. This blueprint mandates the Zynq SoCs to define hardware behavior with 100 nanosecond safety response times, requires 1200 VSES to enable extreme power densities of 20 to 30 kilowatts per liter, and insists on EtherCAT for microsecond precision in multi-motor coordination, which is necessary for world-class torque vectoring control.
The Powertrain 5.0 specification is a framework for technical dominance. It's a detailed, aggressive, and, I believe, essential mandate for any new team seeking immediate competitive relevance.
This raises an important question for you, the learner, to consider as you digest this blueprint. We noted that this specification intentionally leaves significant computational resources unused on the Zynq SoC, particularly in the FPGA logic cells. We've built a platform capable of handling current loop control at 100 kHz. As this platform matures, what immediate future integration will define the next leap in FSE competitive advantage?
The answer lies in leveraging those remaining resources to deploy true artificial intelligence, specifically integrating complex neural networks into the Zynq PL for motor state prediction. This means moving beyond reactive control, simply reacting to a measured current or speed, to an anticipatory strategy. By using AI to estimate unknown parameters in real time, predict component or motor degradation, and adjust control strategies before a failure or an efficiency drop occurs, you achieve a level of control that is truly intelligent. That leap from hard real-time control to predictive, anticipatory optimization, that is the next level of competitive advantage in Formula Student Electric.